just finding this extra help, I think. Just wanting to, in case any of you guys needed that. But yeah, and a little about me, about my OChem stuff. I've taken all the OChem classes with lab. Yeah, enjoyed them. And I'm currently a TA this fall for the lab at UW-Madison. Okay. So again, these are honestly some of the same resources I provided for OChem 1 that I recommended. But for OChem 2, the most important one, and I have it listed right here, 10 out of 10, is going to be your practice problems, discussion sets, things you work in discussion. They're like in OChem 2, I can't stress this enough. You do a ton of more reactions, and so you want to get as much practice so you see all different kind of like ways the compounds that you will learn react. Because let's say we talk about like like just like thiol, right, which is basically an alcohol but with an S instead of an O. It can react with so many different types of ways, with so many different reactions, and so just getting that practice of like drawing out all the different types and those practice problems. I'll also provide some practice problems too afterwards on that. But that's super helpful because then on exam you feel more ready. If they're giving a problem that's like they might have gone over, you've done so many and you've already understood the concept of how the reaction occurs, what concepts what are you supposed to understand with like the bonding, with the reaction itself. So definitely important to go over practice problems. Okay. Next up, again, I also shared this organic chemistry tutor on YouTube. Awesome. He is great for OChem 2. I think he's a little bit more helpful for OChem 1 because there's a lot more concepts occurring. OChem 2 is a lot more just reactions, but he's actually really helpful with lab. He talks about like the spectras and things like that are really, really helpful, for lab, and talks about like, things like that. And also goes over some of the hard reactions in OChem 2 that you just might like not really understand, or your instructor might not go over, but expect you to know. So he'll do that. So I recommend that if you just wanted to, if you had any trouble like with any like reactions or topics in your course. And then office hours is huge again. Knowing what your professor expects is important because again, every professor is slightly different in the way they present, topics, the way they want you to know things. So understanding like if your professor really enjoys talking about the discussion of like pi conjugation or like steric, something like that, or stress those kind of concepts, or rather if he really stresses understanding like enantiotopic, diastereotopic properties of H atoms, something like that. That's a good way to understand what he or she's looking for in office hours. And yeah, again, the book, read part of it. It's a good book. It's more helpful to OChem 1, like kind of like the organic chemistry tutor, but it does have some pretty helpful stuff also for OChem 2. And yeah, and then my advice is same as the OChem 1, but stay on track. And honestly, like my study didn't change with OChem 2. It may be more reactions, but if you consistently review 1 hour a day, and I know it's like it seems easy, but again, it's like you after a long day of like other work, schoolwork, lectures, all that stuff, attending that, it's hard maybe get 1 hour, but I can't stress it. Just like try to get it, and if you only get 45 minutes, it's okay, but keep like a solid hour to 2 hours just to review what you learned or what you learned a few days ago. That's gonna be really helpful again when you take your exam. And then obviously studying at least 3 days before that. That's kind of like my golden rule: 3 days before test, a couple hours that each day. So then on the last day you feel prepared. You're not stressing. You're going over maybe your practice exams, things like that. So you're not stressing over like what to expect. So then on exam day you're calm, confident, and collected. Yeah. So yeah, those are the resources I recommend. Awesome to have. And yeah. So what's the difference between Orgo 2 and Orgo 1? And a lot of people kind of ask this as well because, after taking Orgo 1, they're like, oh, okay, well, maybe that wasn't what expected, but what is Orgo 2 like? So like I reiterate again, there's a lot more reactions. If you technically count like every single type of reaction and like kind, there's like thousands in organic chemistry too. But again, you got to condense down reactions. You got to kind of create your, you know, kind of like groups. In this group, they all act the same way, even though you might use a different compound and in a different environment, in a basic versus a acidic environment, but it still uses the same concepts. And so that's the same thing you want to do with OChem2, just like making sure you can group things together so you can save yourself a lot of headache rather than trying to create flashcards. Because I know people do, and some are successful, and but it's just really tough to do things like that. Yeah. So and then as well, you definitely need to know your organic chemistry once. So I wrote this down. Nucleophilic electrophilic reactions, those are SN1, SN2, E1, E2, unbelievably important, because even though you might not explicitly do SN1, E2, E1, E2, or SN2, nucleophilic electrophilic reactions, the concept is so important to understanding that like this compound that is, wanting electrons is going to, take electrons from this compound that wants to give up electrons. And so that's basically what OChem is, like, and all reactions are just like two compounds that can work well together in, giving up electrons from one to another. That's kind of it. And acid bases, again, huge. Knowing your pKa's, the lower the pKa, the lower the pH, because pKa's are used every time in the reactions in OChem2, because you get a lot more things, like then you have to understand, like, well, in this reaction I have this compound that's maybe slightly acidic, it's pKa maybe 8, but then you have to understand, like, in this environment, is that okay, or do I need to add another compound to allow this reaction to proceed, things like that. So making sure you understand acid bases, looking at pKa's is huge again. And obviously, again, pi conjugation, hyperconjugation, those concepts are tough. And still, it's just like, no one truly knows, I guess, unless you really study PChem and you have a huge understanding of wave function. It's really tough to understand pi conjugation and hyperconjugation, but those two are important. Pi conjugation being that you have, either a lone pair next to an empty p orbital, and a lone pair isn't a p orbital, and then it can donate to that empty orbital, allowing for sharing of electrons and that stabilizing the molecule itself. Hyperconjugation being that, all molecules have a empty orbital that can be stabilized by a nearby orbital. Same thing, except it doesn't have to require p orbitals. Like for pi conjugation, it can require sigma orbitals, other orbitals like that. So those two are really important. And then I never, honestly, with like my students, or when I was a student, like in Orgo, I never stressed memorizing compounds. But in OChem2, it can be kind of difficult. Because there's a lot of different type of compounds. You should definitely just kind of know the main names, that the ones that maybe like go over a lot in lecture, kind of like, what an imide is, or an amide, or an imidazole, like those kind of things. And honestly, I say that if you practice enough, you honestly don't even need to memorize at all. Like, spend time memorizing, because you will become so familiar with the names you doing, going through practice problems, videos, things like that, that it will come naturally to you. And that's when you kind of know you're ready to like take your exam to do well. Okay. And so synthesis problems, if you guys take Orgo 1, you probably know synthesis problems. They're definitely one of the most difficult things about organic chemistry, because you're like, well, I have so many reactions I can use. It's, you never get the same molecule on an exam, the same product in unit form. So, and especially with Orgo 2 or OChem 2, I don't want to say Orgo 2. That's what we say it here in Madison. There's a lot more reactions, meaning there's more possibilities for synthesis. meaning, and I'll kind of like maybe walk through what you guys need to do for like, practicing synthesis. It's so difficult. I know practicing synthesis problem because you will not get the same synthesis problem on exam that you've been practicing. I guarantee it, because they won't they just won't give it like the same thing. But there's a lot of, once you can kind of like look at the reactions more and understand like, these two reactions are awesome for adding a carbon chain if you needed to. So when you saw like another on your exam, if you needed to form something with an extra chain, you're like, oh, well, I kind of know these two reactions can do that. So that kind of shortens your, a huge range of reactions you can use to create that product on your exam that they ask for. Okay. Yeah, and then Orcam 2 contains lab instead of Orgo 1. And lab is honestly one of the most is really important because I'm sure many of you are pre-health, maybe pre-med, and you would definitely should know like those basic chemistry laboratory skills and spectroscopy type problems later on we take exams. So those are really important. We'll go over those two actually today, some of the basic laboratory skills that you should know. But yeah, okay. So that's kind of it for what I have for the slide. The next slide I'm going to go to is the OCHEM skills you should know. So this actually is all the lab skills. We have separation, distillation, reflux, drying agents, TLC plates, and washing purifying. Today, I thought about maybe going over some topics about organic chemistry, like the reactions, but I figured like it wouldn't be helpful to share like reactions with you guys that you haven't learned yet because, I mean, you guys will forget it right away, and in like a 20-minute session of like talk about it won't really be helpful. So I'll just share a few of the problem sets later on that you guys might be helpful to you when you guys do learn reactions and things like that, and some of the notes I have about it. But I thought it's good to talk about some of these laboratory techniques. And so, some of you may not get the chance to actually do these in lab because, if it's online or something like that. So it'd be good to talk about them. So what I'm going to do is I'm going to try to, let's see here. Since I'm not sharing the screen, I can actually just talk through them. I will share the notes I have for you guys about each one of these, but for, I guess, maybe not to drop to like lose Wi-Fi again in the last session, I will just talk through each of these. So if any of you guys are OCHEM lab, you might know some of these techniques already if you guys started earlier. If not, yeah, we'll go through them. So separation, sorry, someone talking?
Yeah, I was just saying you can share your screen. I think your Wi-Fi is fine now.
Okay. Sure. That'd be fine. Yeah, we can go through that then. Yeah, hopefully it doesn't cut out. Okay. Let me then try and get that going. I'm gonna turn off my video then because I'm gonna convert this to a tablet and share. All right. Share screen. Yes. And let's go to here. Perfect. All right. Awesome. And I think what you guys are seeing are, yeah. Alexis, can you confirm that you're seeing my screen?
Yep, everything looks good.
Awesome. And then voice is okay?
Yep.
Whoops, this is actually, yeah. Okay. So what I'm going to do is actually add a page and talk about techniques. Okay. Just I have that. Okay. So, all right. The first technique I want to talk to you guys about is separation. Now, this technique is actually quite simple and effective, but sometimes you get a little mixed up with like it's occurring. So let's say we so I'm actually separation, and basically, let's say you had a molecule or molecules in a flask that contain, you know, acid, base, and like a non-polar compound. Okay. So in this case, yeah, like let's say like we have like this carboxylic acid with an R, base being like maybe NH, and I just want to make benzene. So we have like a bunch of, and a lot of times like organic chemists to purify something, or let's say like after reaction occurs, you might have a ton of other products you might not want. So you're like, oh, I need to separate. I want to just get like the acid, the base, or a nonpolar compound. So what you do then is, and I'm gonna be very generic with like, um, molecules and like things like that. But so you have your starting materials of like your acid, base, nonpolar compound. Then what happens after is, so essentially, what if I added water? What happens? Well, in the new flask, right? We're gonna create almost like it's kind of cool if you like watch the layer occur if you had the chance to, but and then like say this is the top layer. You basically create two layers, one being obviously non-polar and one being polar because of water. So kind of like when you add oil and water, they separate immediately, and you can see that layer. Same thing happens here. If I add a ton of water, the acid and base, which can dissolve in water because that's how they dissociate, are going to be in here. I'm gonna write that right here. Acid plus base, and then the nonpolar is going to be right here. I'll just call it nonpolar, right here, and then we actually plus water. So now we've already separated two of them, like in half. So like the nonpolar and now kind of like the polars. So what we do then is, oops.
I think your audio cut out, Anton.
I just accidentally turned off my laptop. I don't know. Yeah, sorry. I was on a roll too. Okay, yeah. So now we have two different layers, right? And what's nice is then we can, like, after we make sure that they're separated, we pour out. So I'm gonna draw this black, maybe better. We're gonna like pour out, and actually not really pour out. It's kind of like yeah. Well, actually, we'll call it pour out. But in these like flask in your chemistry lab, we have this opening funnel. Kind of looks like this. I'm terrible at drawing, so from here that you turn this valve and it opens and it can drop stuff um, into a beaker, and basically what's happening is you open it and then you only let down one of the layers, and so since your polar layer is going to be more dense than your non-polar, which is why like you see oil float, you're going to collect out your draw it in red here and write down and pour out. You collect, we call it your aqueous layer. Now we have your acid bases, and in the flask you have your non-polar. So that's what's left. Technically we've isolated our non-polar, and then we can do it. We can do the same process again, add some water, non-polar, and then try to like clean it up in case there was any like other aqueous molecules got stuck in the non-polar, but then keep purifying like that, and then isolate non-polar. Now we have acid base. So then how do we solve that? Well, what you can do is, so what's cool about acid base is that when it's deprotonated, like so, right? So I just want to share like, so let's say we have our carboxylic acid, and then deprotonated, so minus an H plus, it's going to be a carboxylate, right? So we formed this in water. It's gonna there's it's kind of an equilibrium type between both, but and I don't know if you guys know this, but acid and bases, if they actually aren't deprotonated, they are its own organic molecule and they can precipitate out. So let's say, you have acid base here, and I'm going to draw another arrow. Let's say we add base. So add base, right? We're increasing pH, and thus all of the acid in there is going to be deprotonated, right? So it's going to be, what do you call it? It's going to be all, I'm draw it in pink, purple again. It's all going to be like this, but then, nope, all going to be deprotonated. Did that. And then your base is actually all going to be, just your base is not going to be protonated at all, because it's basic environment now. This right here, very soluble in water, so it's soluble in water. Your base now, the base that you wanted, is like it can form own layer from water. I mean, some of it will be aqueous in water, but because it's organic now and not ionized, if it's ionized, it's very dissolvable in water and move back and forth, but now it's not. So we have, we can isolate. Now we have one that's going to be in the aqueous, and then one that's almost going to be in like above, I wouldn't say non-polar, but it would be like less soluble region. And so this size will be more dense, and it's going to be with all of the aqueous base that we added. And when we add acid base, I should let you guys know that's kind of, you want to be strong, because adding weak won't really do much. You basically create a buffer, as you guys probably know. So this is gonna be soluble in water / it's gonna be in strong base here, and this is actually separate on top. And so you see another layer form, and then you can basically do the same thing where you guys isolate, where you guys pour, turn the valve, take out your carboxylate that's soluble in your strong base and water that you added, and then you're just left with then your acid. I mean your base. So that we isolated that part, right? Then we still need to isolate the acid, which is now carboxylate. So then we just have to add acid, and then acid, because it's strong base, a ton of acid. So then it can basically become, and let me get that in purple. Go back to carboxylic acid, and then now because we added acid, the base is now going to be aqueous with the acid we added, and so it's going to be separate, and it's going to be, we'll call it forming your own layer, and now that's isolated too. So through that method, which is called separation technique, by aqueous layers and solubility, we can isolate nonpolar to acid and base. So that's something actually really nice that you'll see in your lab talked about. A really basic lab technique that's honestly pretty you kind of understand every step. It's it makes sense and everything. So hopefully that helps. The next and then we'll go over questions at the end if you guys have anything about this. But the next one I want to talk to you guys about was distillation versus reflux. So distillation versus, and honestly, because the reason why I gotta bring both of them together is some people get them mixed up, or they think they're almost the same, but they're not. So, all right, distillation. I hope I can draw this well. It's gonna be kind of terrible. So let's see. You have flask that's connected to this thing like that, and then there's this, and then it's gonna pop into another flask. And so this is a lot of the time, this is another kind of purifying technique that's amazing to use in organic chemistry lab. But you get your product, but let's say it's again with a lot of other products, and sometimes it's not easy to use separation because it won't separate as easily, and you won't get that clear layer you can see, so you can filter separate out using that method. Distillation is where it can work better. So one example to use is like when you guys form like in your lab, common lab is like forming alkenes, right? Kind of like it's a gasoline type molecule, type compounds, and it's those alkenes. So, but a lot of times we had to use like water, other things, bases with it, so it won't be isolated. But the cool thing about alkenes is, so let's have an example where we have an alkene with like plus like other like aqueous products, right? And so like let's say like these products might be like alcohol, water, that. Well, water and alcohol actually have a boiling point that's a little bit higher than alcohol. Alcohol actually has a boiling point of around like room temperatures, honestly, kind of like a little higher room temperatures, like 37 to 40, I believe, Celsius. And these ones technically have like one around like 100-ish type thing. So what's cool is most alcohols, some alcohols have a little lower, but the ones you usually deal with in these, basically you put your products like that contain your alkene that you might want, plus your other unwanted byproducts, put them in a flask, and then you're going to heat up this flask. So I'm going to draw like a fire right here, but actually it's a hot plate, it's not the actual fire. And you probably want to use Bunsen burner too. It's just kind of like primitive, but you'll definitely use a hot plate or a sand bath type event. But you're heating up this product, right? And you're heating up to the point of the boiling point of this alkene. So just the alkene boils. And once the alkene boils, it's going to go up. And then once it hits this region right here, we actually run cold water through this. And if you think this tube, this is a little confusing. This tube right here is a tube, but it's also like, let's see here. So it has like, this part right here is connected to water. So water is running through like this outside tube of this like whole tube right here. So it's cold water, so it's cooling it down. So as soon as it hits this region is cool, right? And it's going to condense back to a liquid form, right? So this is going to be like liquid. This right here is going to be gas for this, right? Rising, heating up, and then condenses back down because the cool water kind of running through and cooling this region. Condenses all the way back down to now we just have our isolated alkene. So that's distillation. It's technically, isolating stuff by boiling point, differences in boiling point. Because we know that our product has a lower boiling point. We can just heat it up only to like a little past the boiling point. So you make sure all of it's boiled off, and then condense it down, and then stop it, collect your product, and you're good. And then usually sometimes we keep this in an ice bath, just so it can stay cool and not go back out. So that's distillation, right? Reflux, on the other hand, is similar. You're heating up something, but it's different in the fact that you're not separating by boiling point. You're just honestly trying to get that reaction faster, like increasing the rate of reaction. If you guys remember from Gen Chem, we can increase rate of reaction by temperature, and that's exactly what this is doing. So this is almost like if you think about this distillation kind of like apparatus, it's that without a collection like flask at the here. You still have product right here, right? So you have your product, but no, actually, you technically here is the difference. You have your reactants, right? Your reactants, and for reactions that like that take a long time, or chemists don't want to wait 2 days for a reaction to occur. So what they do is they increase the rate of the reaction by heating up. And I'm sure you guys know that heating
heating up the reaction will increase the reaction, especially if it's, if it requires energy, if it's endothermic. And so that's what reflux is. You're heating it up, and then it boils, right? Same thing we see boiling. And then right here, we have cool water. We have, I'm actually drawing blue. We have cool water running. And then that's going to condense it back down to your liquid form right here. And you're constantly doing that. So you're basically allowing for this a lot of high heat, basically where the molecules are at the gaseous stage most of the time in this area. So in this area, we're in your gaseous phase. And you know how in gases, they're bouncing all over the place, they're moving really fast. You increase the rate of reaction because you have a lot more molecules that can move faster and hit and collide at the right time to overcome that high activation energy barrier, overcome the transition state to form the product. And that's exactly what reflux is. You're basically increasing the temperature of the reaction and not really lowering the activation barrier, but overcoming the activation energy barrier through temperature and forcing the molecules to be in the gaseous phase for a reaction to occur. And then finally, then the reactants are going to be later on converted after reflux. They're going to be hopefully all converted to products. And then it would take a lot less time than it would just waiting in a flask at room temperature for the reaction to occur. So that's reflux versus distillation. Okay. And the next three I want to talk about are pretty easy in terms of understanding. They're less, they're going to be drying agents. They're going to be, what do you call it? Name. Oh yeah, TLC plates. That's right. I'm always thinking there's different kinds. You guys are probably going to know what these. And just washing, purifying. This is honestly, you guys probably know what washing, purifying is. I just wanted to bring it up as a possible lab technique. Drying agents. When you guys add a bunch of aqueous stuff to your product in OChem, and your product has a bunch of aqueous things, you want to add drying agents kind of like MgSO4 that can basically form a solvent, kind of like a solvation complex with water, basically taking the water with it, forming new bonds with the Mg and water, and then it forms after it's going to so it's going to react with water or aqueous stuff, and then it's going to basically form what do you call it? Clumps. We call it clumps or precipitate. And then you basically filter out. Yep. You can use your vacuum filtration. I don't know if you remember Gen Chem, where you put it through a filter and suck it with a vacuum, and then you just get your product. Get your final product here. So that's what drying agents do. You can just help dry material, so then you can test maybe your percent yield, which is honestly unimportant in OChem lab, but just in case it's good knowledge to have, or just if you want just product to analyze, that might be easier. Drying agents do that. TLC plants, ooh, I love them, but they're kind of weird. So basically, they're literally like a piece of a paper, a small thing. You have you have a dropper, right? Then you're gonna drop one drop right here at this location, one at here, and one at here. Okay. This drop right here is with just product. So call it A, B, C. A is gonna be not product reaction. I'm sorry, my bad. B is gonna be halfway in reaction, and C is going to be your products. So when you have your reactants, right? You're gonna have a TLC plate, which is basically, I don't want to make you guys confused, but it's honestly, this plate is a lot of times it's silica. It's a solvent that is unreactive with many things. So you dip a little bit, right? You dip like one thing right here, and if you and if you put it in, let's say like another solvent, your uh, your reactant you put right here. So reactant before the reaction, like before you actually combine reactants, you add a reactant right here, and then it's gonna place itself right here, and because maybe it's like at this level, this is where it's fully if it's like if it's very nonpolar to the solvent it's added on this plate on this like paper. But if it's middle, like you don't necessarily have to know where this placement is, but you add a reactant and then you put it in a solvent, it's gonna kind of like climb up to this level and be a dot right here. This and then let's say and then run the reaction, right? But this kind of like monitors like when the how long the reaction might take, and if you got other products, because then you can do a test again for this side for B, where you assume like might be halfway during the most molecules reacted. So now you should probably have your reactant still, right? Because not all reactants have converted to products, but then you might have a new product that's right here. So that tells you have both, right? If you have 2 dots versus one just shows your reactants. 2, maybe this is a product, and this is your reactants in R, and this is R. And then C, at the very end, you should definitely just get, oops, not this bar here. You should definitely just get product, which is going to tell you that like you have no more reactant, and then you are completed. You have, then you can move on to the next step. So that's kind of that for TLC plates. And then washing purifying, I'm just gonna go briefly. Same thing as like a separation technique above, but it's going you can purify. Adding like acid bases to change things from the aqueous layer to the organic, and then separate that using that method. Washing, a lot of the times you can add like washing agents to that will take out kind of like drying agents that take out anything that is unwanted. And these, you don't have to know the agents, but that's what you want to do, because a lot of times we just want a pure product, or as pure product we can get. So those are kind of the main things with those skills you should know. And then I'm going to reshare back to the presentation because I think it's a good idea to get you guys kind of like interactive, ask questions at the end, spend time with that. So I'm going to try to move fast and get it going. Give me 1 second. I'm trying to.
I can share my screen if that would be easier.
Yeah. Actually, yeah. Can you share your screen then? Maybe better. Perfect. And then you want to go to. Awesome. I will go over this as well, but I do have slides for these, so I just want to heads it up. I'm like notes for these. You will have to go over these. It's huge in OChem 2 as well, the beginning especially, because they're helpful because they basically tell you what bonds are in the molecule, what's interacting, things like that. Spectroscopy is weird. I don't want to go in too much in depth. It can be confusing, but check out the notes I'll present later on with these. It's going to be, just talking about like what each one does, and I'll kind of explain a lot more like condensed, concise information about each one. But yeah, these are definitely check that out later on. I just want to bring all 4 of these main that you'll probably do in your class, and then you can go to the next slide, Alexis. All right. So, so I just want to, for kind of end, I definitely want you guys to ask questions about what I just talked about, anything else about OChem 2 lab. And I just want to be like interactive. Want to help you guys like just answer any questions, confusion, clarification you might have. So definitely put in the chat if you have anything you want to talk about.
And you guys can scan the QR code to get member points. If you can take a screenshot, that would be great. But if you can't, that's totally fine too.
Yeah. So go ahead. Feel free to ask any questions in the chat about anything we talked about. If you want to talk about something else, I know there's a lot of things that I could have gotten over, but I just wanted to go over techniques. I thought that might be easy to know, and especially now if you don't have if you're not seeing experience in person, it might be easier just to talk over them, kind of get a preview of what they might be. So yeah. Uh so Ro, did you want me to share my notes like just I just wrote? The notes that I'll be sharing notes later on, containing more OChem 2 information with everyone in on Slack and everything and in the Google Drive. So I'll do that. But if there's something specific you want to talk about, I'll feel free to talk about right now. Hope that helps. All right. Cool. Any other questions? Yeah, floor is yours. Um,
Hi, I just have a quick question.
yeah,
So,
go for it. I'm sorry, I can't. Yeah, go ahead.
okay, so I kind of missed like the Orgo 1 workshop,
Mhm.
but I was wondering like if you think it's a good idea to invest in like clutch prep for it.
What thing? Sorry,
Clutch prep.
I haven't heard of that. What is that?
It's like this whole website where I'm pretty sure you have to like buy a membership or something for it, but it's like it goes through like your actual class for Orgo or whatever course that you're taking, and then it works with the textbook and it, like somehow knows when your exams are going to be and stuff like that, and it gives you videos on a certain chapter or something like that, you know?
Yeah. I mean, since I haven't taken, I can't. I guess I can't necessarily endorse it, but it
Mm-hmm.
does sound like it might be helpful for you to, like, it provides more access to resources and I guess keeps you updated with like, yeah, your exam things and like what might be on there. If it's something, yeah, your instructors might recommend, it might be helpful. Honestly, yeah, it might be good just to maybe if like you know about it, maybe ask your instructors about like if they also think it might be helpful because it might be like great itself, but again, you have to make sure that the information that they're showing corresponds well with what exactly is being taught in your class, because that's the most important thing. Like I know like in all different schools, some reactions aren't covered, some are covered very heavily versus some like they just go over the bare minimum. So I think it'd be it sounds like a great idea if you want to do it, but definitely make sure it would correspond well with what you are expected to know in your class at your school. So yeah, but yeah, I hope that helps with that. I I would also stress too, making sure that you don't use too many resources. I know sometimes it's like in like it's help like you want to like find like, oh, I want to like have this, have this, but also like making sure like like there's just have a few good things that work for you, right? Because you're not gonna have time to do everything and like have every type of like prep thing to work with, but just like having the few good ones and then work diligently with those. I think that's honestly like your best route there. So just in case, yeah, just a heads up in case, like, yeah, things like that. But yeah, hope that helps.
And
Uh,
just
yeah,
one
go
more
ahead.
question. I'm sorry, I'm cutting you off, I think.
No, you're
Or
fine.
okay, did you happen to drop anything for Orgo, like as in like resources? Because I kind of missed that part.
Yeah, so I'll be sharing some of the resources later on. I went over some like notes and some things in the previous session that you can look over. And this whole like it's recorded, so if you want to check that out. But I'll be sharing some like problem sets, and then I also have on this presentation we have a link to like the overview and kind of like about everything you might do in Orgo 1 that I
Okay.
shared. So you can check that out. So yeah, we'll post that definitely in the Google Drive and everything.
Okay,
So
thank
of
you so much.
Yeah.
course.
I think we went over like doodle in the membrane. Let me
Mhm.
see if I can pull that up. But they're just basically infographics. Let me see. I think Danny sent the link in the chat. Um, can y'all see the screen?
Oh.
Sorry?
Yeah, I can see it.
Okay, awesome. But yeah, these are just like infographics about stereoisomers. Like this is more so like Orgo 1, but it could be like a nice refresher if you're going to Orgo 2 and you forgot some stuff from Orgo 1. And
Yeah.
I think Danny also shared the Orgo as a second language textbook in the chat, if I'm not mistaken.
Mm-hmm. Yeah. So yes, I think Samuel has a question. I'm not sure if I say your name right. About yeah. So what's the best way to organize a reaction guide for OChem2? So yeah, this is actually a lot of people. Yeah, like always ask that. I think my professor is really great at actually explaining how to do it. So and actually I'll share some of the notes later on about like maybe like some guides that kind of what I divided up. But yeah, so when you want to classify like reactions together and everything, write down what I would say like what they fall under, right? Is it substitution? You know, is something being replaced? Is like is it, you know, is something I don't know if you know this yet, Samuel, where you know you attack uh at the, you know, like by like you know nucleophilic electrophilic reaction type thing, and so like classifying like by like what exactly the reaction does, the mechanism is helpful. So like you can like list down like those kind of types of things, and um condense like, okay, well this reaction actually does that as well, so then it falls under that, and then under each one then classify it as like what compounds can it react with and in what similar way, right? Does it react with alcohols the same way as it does with thiols? Does it react with you know, alkenes the same way as it does alkynes? So those kind of things. I'll share a guide, like my guide that I have like for reaction guide, Samuel, if you want to look at that as well. But that's what I recommend to do. And also for synthesis problems, I know it's so tough to like, you can't really prepare for what the synthesis problem might be in your exam, like what product you're forming from what reactant. But what I recommend is doing practice. So like you draw a random molecule, right? And then it's kind of like a flow chart. So like you have in the middle of your paper, draw arrows. One reaction, what might it form? Oh, so you form this new product, this alcohol. Then drawing out more arrows, what other types of reaction can occur? And then keep like branching out from the middle and keep making random molecules. And then seeing it, eventually you're seeing like, oh wow, I can, going through this step here, I can form this alkene from this acid, or I can form this ester from this acid, something like that, right? And then you kind of recognize a lot of the key reactions that get you places, and that's really helpful. That I found actually, and what my instructor recommended to do, because yeah, it's difficult to do synthesis problems like that, but that is definitely something in to work on and try. I recommend to do for synthesis problems. But yeah, I'm glad. Yeah, I hope that helps. Let me know if that works for you. And Danny asked, would you recommend to buy molecular model kits? So I think it's useful for OChem 1, definitely not for OChem 2. I think it's just like, it's just almost too long to build model kits for so many reactions and more complex reactions in OChem 2. Molecular model kits are great because you can see exactly where space is in the molecule where something might attach to, right? You can see if like the sterics, where that might be. You can see how like, you know, if it's, you know, how the orientation looks, things like that. But a lot of the model kit, I think that's a lot more helpful for OChem 1 because that's the main part where you're like learning bonds forming, things like that. Orientation, stereochemistry of molecules. That's helpful for that. Here in OChem 2, we have a lot more reactions. And the main thing is understanding like when we add this compound, what do we form? How do we form it? And from that molecule, where can we go next? So model kits aren't as important, but you can always, I mean, if you have your model kit from your other semester, Orgo 1, definitely keep it. If you want just to have that in case. I don't think anyone really used it that I know of, and I didn't really use it. But yeah, don't let that, you know, deter me from, you know, like allowing you to use it. But I just don't think it might be more time consuming than actually helpful for OChem 2. Yeah. Any other questions you guys have? Um, I know I went through a lot of information too, so yeah, and yeah. But yeah, okay. So what else would I maybe recommend to just in case for you guys? Yeah. So yeah, OChem 2, just really, yeah, it's a lot of reactions. but honestly, like, it's gonna take you, good organization skills and understanding like, this is the key concept. We're moving on. It was basically the same. Yeah, I use different compound. Yeah, it's in a basic environment. Yeah, I form a slightly different product, but the whole kind of idea is the same. So keep that in mind. Like, don't get too like worked up. Like, oh wow, like there's like so many reactions. Like I just learned 10 today, but understand like, oh, okay, well, there's always a key basis. And honestly, I would say it's like the whole edit OChem can be deduced down to an orbital donates electrons to another orbital, forming a bond, and that's it, honestly. Or breaking, vice versa, like the orbital breaks from another orbital. And yeah, and the whole point is just like making sure understand like what orbitals would match well with other orbitals. And orbital again being area of space where electrons are, because electrons are what form bonds. And then understanding the fact that like what role plays the fact. Is there a bunch of sterics or a bunch of molecules that are crowding so you can't really bond? So is that not viable reaction? Is the stereochemistry wrong where, it won't create, the enantiomer you want for the product? So like those kind of concepts you get from like OChem 1, keep those in mind again. Like I said before, for OChem 2. That's kind of like the main goal of instructors wanting to understand everything, kind of using concepts and applying them at a higher level. So yeah, any last questions? I can be here for a little bit. If you guys have any other lingering questions, if not, yeah, I thank you all for attending the session. Hopefully that helps. Please let me know if you guys later on have any questions come up. Obviously, I'll be sharing some resources with you guys through our Slack channel, Google Drive, things like that. But yeah, thank you for attending again, and hopefully this was helpful. Appreciate it. Oops.